Hello. So today we consider Gaussian quadrature. Which is extension of what we did last time. So essentially the idea was that we want to approximate the integral of some function in a given interval using some values of this function inside the interval, inside the interval, which we call x0 to xm. So m plus 1 point. So we take m plus 1 point, compute values, and at this point and define the integral as a linear combination. So the goal is to compute this gf, which is exact integral of the function in the interval, and this we approximate by this linear combination. So it's it's convenient to put the size of the interval outside, and then it's a sum over all points, linear combination. So there are coefficients by values at these points. So what we did last time, Newton-Cote formula, is that when points x are fixed, so what are the fixed and they are fixed in equal distances, so what are the coefficients? So the idea was that we take coefficients in such that the formula become exact on certain polynomials. So the equidistant distribution of points is important because it corresponds to many ways how we compute a function. But we can, in Gaussian quadrature, we can do better if we now optimize. So we now optimize. So last time we optimized just weights. So now we can optimize both weights and points. So we optimize both weights and position of the points, right? So how many of them? So we have m plus 1 weights and m plus 1 points. So it means that there are 2m plus 2 free parameters. And this means that we can expect that, so define the Gaussian quadrature Q of f is exact for all polynomials. So we define the Gaussian quadrature as the quadrature which is exact on all polynomials of degree. So we have 2m plus 2 free coefficients, which means that we can afford the polynomials of degree smaller or equal than 2m plus 1. So this is exactly a polynomial that has 2m plus 2 free parameters. So our goal is to show that they exist. We also will show that they're unique and find them. So that's an idea. So so the construction is actually explicit. So what we do, we start by taking polynomials. So take, first of all, monomials. So 1, x, x squared, and so on, and construct orthonormal system of the normal set P0 of x, P1 of x, etc. by Gram-Schmidt procedure. Gram-Schmidt process. So remember, so what means orthonormal? It means that scalar product of the two, which is defined in our case as the integral between a and b, pj x, pk of x dx, and it should be delta jk, so it's 0 when j is different from k, and it's 1 when j equals k. And Gram-Schmidt process, if you remember, so what we do, we first, P0, we take 1 normalized by coefficient so that the integral is right. Then we change x by subtracting the previous one, the 1, so that it's orthogonal, and normalize. Then we do the same for the square. So we first make it orthogonal by subtracting the previous and then normalize. So there is this process. So you can directly construct this set of polynomials. Just remember this Gram-Schmidt process where we discussed this, how to construct an orthonormal basis. Okay, and we will use this basis. So if you take a book, book actually considers a slightly more general formulation. More general formulation in the sense that they consider different scalar products. So you can consider, so one can consider a different integral. So the integral with a weight. X for given function of weight such that it's positive in the inside the interval. So in principle, you can use the same orthonormalization process, but with different scalar products. So in many cases, it's important. But anyway, we will not do it. Let's just stick to the normal, the usual integral of the usual product. Okay, so we need to prove some things. So the first thing we will prove will be proposition which tells that the polynomial Pj of x has j simple roots inside the interval. So, well, every Pj is a polynomial of degree j, so it always has j roots, which can be complex and they can be repeated. So the statement tells that whenever you do this orthonormalization with this product, all roots will be inside the interval, and they will be different. So this is somehow this very regular structure of the roots. So in other words, it will change sign j times inside the interval. So every simple root means that the function changes sign. If the root is not simple, it's possible that it just becomes 0, but sign is not changed. Yeah, like x squared. The proof. So these are rather elementary stuff. So what we do? So let's just take this polynomial. So what we know? We know that Pj it's orthogonal to all previous ones, right? So it's by construction. So Pj is orthogonal, so it means that scalar product is 0. So what we assume? So let us denote by, so let us denote all points inside the interval. All points at which Pj of x changes sign. So let's just, it's a function, so it may change signs at certain number of points. In principle, in general, S number of these points it cannot be bigger than j, right, because of the root. So what we need to prove is S is j. So we need to prove that S equals j. So how you prove? You take these points and construct the polynomial which is exactly has roots at this point. Right. So what you can see first is that if you take scalar product of P and Pj, so it's what? It is integral P of x, Pj of x. So what you can see that they both zeros, they both take 0 at the same points, right? And in between points, they have the same sign, right? So it means that it's certainly not 0. So we construct it's certainly not 0 because product is either 0 or it has same sign everywhere, and it cannot be 0 everywhere. So it's certainly non-zero quantity. Okay. So, but if S is smaller than J, in this case, degree of polynomial P is smaller than J. But if degree of the polynomial P is smaller than J, that it should be orthogonal to J. Yeah? Because if degree is smaller than J, then it's linear combination of the previous polynomial. They're all orthogonal to Pj. So it means that Pj should be 0, which would contradict to what to our constructions. So it means that S equals J. we proved. So we proved that whenever you take this Gram-Schmidt process and just construct polynomials, you construct very nice polynomials. So at every point they are, or at every j, they have all their roots are real and placed inside the interval. So now we can prove the theorem. Which tell that for any m for any order, so m should be starting from 0, no? For any m the Gaussian quadrature is given uniquely by points, so nodal points xm, which are roots of Pm plus 1. So we just proved that Pm plus 1 has m plus 1 different roots, which are strictly inside the interval. So we take nodal points exactly at the roots of Pm plus 1. And the weights which are given explicitly. So alpha j is 1 over b minus a integral ab over Lagrange polynomials dx. So Lj of x, just to recall that this is product of all so it's a polynomial which is obtained by these ratios x minus xk, xj minus xk. So Lagrange polynomial. So you take the integrals in the given interval, divide by b minus a, and this gives you weights. This gives you weights. So this is theorem. So we'll prove. So that's by the way question that last time was given. So it tells that if we want to approximate integral by these linear combinations, and we want the best way find the best way how to do it by choosing both coefficients and points, there is just unique way how to do it. And the points are roots of Pm plus 1, and the coefficients are integrals of these Lj, Lagrange functions, Lagrange polynomials. So how to prove? So we have to prove two things. First of all, that this is Gaussian quadrature, and the second is that any Gaussian quadrature is this. Right? So existence and uniqueness. So all the proof is about checking that the quadrature is exact for all polynomials of degree 2m plus 1. So we should take polynomial of degree 2m plus 1 and start playing with this. So consider any polynomial phi of degree m plus 1, or 2m plus 1. Now we have polynomial of the degree to m plus 1, and we also have polynomial of degree to m plus 1. So we can divide one by another. So remember what means division of the polynomial. So phi can be written as what are the notations? Q of x by, so this is division by pm plus 1, and then the remainder will be r of x. So you can represent any polynomial in this form. So you see that this gives you m plus, you can find q such that you cancel all the terms of degree more than m, and this will be the rest. So q and r are polynomials which have degree smaller or equal than m. So that's, I guess you remember. So we split it into two pieces. And now let's show that all this procedure allows you to compute, to verify that the quadrature works. Okay, so how we do it? So let's compute the integral phi dx. So there are two pieces. First piece is q. Another piece is r. So the first is, by definition, is a scalar product. But q has degree at most m, so they are orthogonal. So we already need only to prove that this remainder has correct value. So now what next we do is that remember these Lagrange polynomials at j of x. So it is it's exactly 1 when x is xj, and 0 when x is xk with k is not j. Just by construction, right? So this is how it's constructed. Which means that what we can do is that, and also these polynomials, they form a basis, right, for the polynomials of degree up to power m. So what we can do is we can just, and this is a polynomial of degree not more than m, so we can just expand it in as a linear combination of these basis elements. So with, and since it's 1, we know the coefficients. So coefficients are just values at this point. So it will be sum over j from 0 to m, r at point xj, which is gives you coefficient to this function. So this is a polynomial, and this is a coefficient which just makes the right value at the node. So this is an exact expansion. And now we substitute it in here. And what we have is AB, call this ABR equal sum over J0 to M Rxj integral AB J dx. And this is alpha. It's exactly alpha times B minus A. So B minus A comes outside, and then it's alpha J R Xj. And the last point is to use, remember that Pm plus 1 at all points is exactly 0. This is how we define points. And phi is Q Pm plus 1 plus R. So phi at every nodal point is this is 0. So it's the same as R at nodal point. So we can just write it as B minus A sum J from 0 to M alpha J phi Xj. And this exactly proves that this is exact, so that this quadrature is exact on every polynomial phi, which has a degree up to 2m plus 1. So what we proved is that QF is exact, that phi is exact. So for every polynomial. So we proved that it works. So we proved that this quadrature that we constructed is the Gaussian quadrature. So now we have to prove the converse, so that if whatever Gaussian quadrature has this form. Conversely, if Q of F is exact, F phi, for any phi of degree small or equal to 2m plus 1, then what we do, take special way, this special form of this phi. So take phi equal Pj of x by product x minus xk for j small or equal, for any j small or equal to the m. So take this polynomial, first this polynomial from our set, and then you put the product of these m terms. So this polynomial has certain degree. So this is polynomial degree m plus 1, and this is up to m. So this should everything should work. So now Q is exact on these functions. So we know that the integral should be the integral should be given exactly by this expression. But you see, whenever you put xj, it's always 0, because we take product of all these terms. So one of these terms is 0, so this is 0. So what we proved, that, so integral of this expression is 0, so we proved that this product is orthogonal to all Pg, to all Pgx for j smaller or equal than m. So this is just orthogonality property, because this times that is 0. But this has degree m plus 1. So what? This has to be degree plus 1, which means that it's orthogonal, which means that this product is proportional to this polynomial, right? Because the only polynomial of degree m plus 1 which is orthogonal to all of them is pm plus 1, or pm plus 1 by any coefficient. And if this is true, then these xk are roots of this polynomial, as we wanted in this theorem. Hence, all xj are roots of pm plus 1x. So we proved that nodal points can, for any Gaussian quadrature, nodal points can be only those. And then, if these are nodal points, this nodal point that the proof which was done before, which it showed that for whenever nodal points are roots, the coefficients alphas should be those which are given in the formula. By this 1 over b minus a. So this we also proved because this on the first part of the proof we proved that whenever points, null points are roots, then coefficients should be given by this. So this second part shows uniqueness. So any Gaussian quadrature, this is the only Gaussian quadrature you can construct. Yeah, proposição é que proposição tells that there are m plus 1 roots, and this we always were needed because we use this orthogonality property to m previous ones. So the number of roots should be m plus 1. So the smaller number of roots will not serve, and this expansion as well. No, yeah, because this expansion. So at several points we need m plus 1 points. Okay, good. Well, just short example. It's just for you to have some. To have some idea what it is. So. Consider the interval from -1 to 1. So a is -1, b is 1. Then we can just compute. There are different ways how you compute points and coefficients. So this I will not give you. If interested, just open the book and look. So 1 point method corresponds to m equals 0. And so certainly this integral is symmetric with respect to 0, so everything will be symmetric. So if it's just 1 point, point should be in the middle, I guess. So point should be at the middle. I will call it Z for this interval. And coefficient should be 1. Yeah? So sum should sum up to 1. So this is the trivial version, and it gives you midpoint rule. Quite a good rule for computing integrals, in fact. It's simple. So we already had it before, but it just shows that for m equals 0, that it was for the open Newton-Cote formula. So for 1 point, so it also optimal, which is somewhat obvious because if it's optimal, it should be in the middle by symmetry. Well, that's not necessarily expected, at least. So now we proved. Two-point case, so it's m equal 1, and there will be 2 points. So the 2 points there is symmetric, so that 0. No, I don't know why that. So let's call it 1. You know? So here it's, for some reason, it starts with 1. So Z1 is minus Z2, so that they're symmetric, and they are placed at 1 over square root of 3, and the coefficients should be equal. They sum up to 1, so they equal 1/2. And then let's give you one more version. M equal 2. So again, it should be symmetric, so there will be 2 points symmetrically, which will be placed at square root of 3 divided by 5, and the middle point will be at 0 by symmetry. And then the coefficients, again symmetrically, first and third should be equal. And this is 5 divided by 18. And the middle coefficient just should sum up to unity, so to 8 over 18. So the only, let's finalize it and then we'll take a small break. Or not. Yeah, okay, small break. We're back. Okay, so another thing to prove about this method is that, so we optimize coefficients, so it's nice to know that they're positive. So another proposition, at all weights of Gaussian quadrature are positive. So you don't need to subtract anything. So the proof, so how you prove it, you take special polynomial. Take polynomial Qj as Pm plus 1 squared. And it has degree a bit too much, so we divide by x minus xj squared. And this division is exact because xj is a root. So it's essentially it's a product of all squared terms except that the j ones. So let's take this polynomial, and this has degree to m. This is exactly degree to m. So let's compute its integral. So integration should be exact by the Gaussian quadrature. So we know that it should be b minus a sum of the coefficients by the values of Qj at so coefficients k at point k, like this. But now you see this is 0 if j is not k. Because if j is not k, this is 0. So we need, so it means that we can take j equal k. So we end up with b minus a sum k0 m. No, there is no sum. Confused. There. There's no summation. It's alpha j. So k equal j. Q j xj. Exactly. And now we substitute the explicit formula. So it is equal to b minus a alpha j and this product. Squared. And that's it. Because you see this is positive. This is positive. This is positive. So the coefficient is positive. So every coefficient is positive. Okay. There is also error estimate of the error that I will give, which is very similar to error estimation in other formulas. So I'll just formulate it, the error formula. I'll just formulate, but I will skip the proof. So if you want to see the proof, you look at the book, or you can just do it yourself. So the theorem tells you that if the function is sufficiently regular, so in that case it should be +1 derivative, so 2m plus 1 in the interval, then the difference between the integral and its Gaussian quadrature is exactly this highest derivative that we wanted, computed at some point psi. It should be divided by just fixed number, and then multiplied by another fixed number, which is integral of this pm plus 1 polynomial squared in dx. And if they are orthonormalized, this is just 1, right? So let's write it like this then. Okay. For some side from the interval. So essentially, there is a very clear the error that we have is directly given by the next derivative. So if you know you have estimated for derivative, you know you have exact estimate for the error of your integration. The proof. The book. See the book. Okay, this is all right. So now a few comments. So important observations. So there is an important difference between Newton-Cote and this Gaussian formula is because for the Newton-Cote formula, so let's write in C, Newton-Cote method. It is possible that the limit as m goes to infinity of the quadrature is not the function interval. So in fact, more points you put in a quadrature, it's not necessarily that it will converge to the interval. So it only, for each m, it has an order. It has the right order. So for each m, if you decrease the interval, you will converge with certain order to the interval. But if you fix interval but change m, it does not necessarily, it's not necessarily converges. So for f, so f should be C infinity in that case, right? It should diverge, I guess, normally. Yeah, it's usually it means that it diverges. Yeah. So in these situations, the not convergence usually implies diverging.
Yeah. I would think that maybe it could just converge, but to non-zero epsilon, right?
No. I think. Well, it may depend on f also. Yeah, but normally it's. I guess it should diverge. So it means that we need this composite procedure. So if with Newton-Cote formula you want to compute integral very, very precisely, so increasing precision, you cannot increase m. You have to cut interval onto the bigger number of subintervals and use quadrature with fixed m inside. So this is the only way how you can really converge to the exact integral as good as you want. So with Gaussian quadrature, it's different. So it works. So you can prove that it works. I will not do it. But limit of m goes to infinity of q f is the integral for Gaussian quadrature, which is very nice because if it converges, so in this case, so we do not, in principle, we do not need this composite procedure. Which means that we don't need to split interval into the small intervals, but instead of splitting, we just take right points with right coefficients. It's slightly costly because you need to compute. You see that these points are usually irrational, so you need to know these points with coefficients exactly. But this gives you a very, very high order method. So with, let's say, whenever you need for composite procedure maybe 1,000 points, you here can attain with 15 points, so that with the same accuracy. So that's, so let's say just, so instead, one can use a single, so Gaussian quadrature on a single interval. With large m. For example, let's take M64, for example. So and this gives you very high order method. So of course, if you go this way, you should take care of round of errors. So a round of errors because otherwise this very high order will be completely suppressed by the order of the truncation. But because as you increase m, very soon the order will be so high that accuracy due to the approximation will be extremely small. So all errors will come from round-off, from computational error. So that's the essential difference. So there are good and very quite a good side of this Gaussian quadrature. So finally, what I want to comment, so give some comments on how to compute. So we consider 3 points. So first will be multidimensional integrals. Second will be infinite interval integrals and singularities. So the first is multiple integrals. So let's do 2 dimensions. Because any other case is the same. So what we want to compute the integral of the function of 2 variables. And let's do it for the rectangular domain. So what you do, so we have a domain. A, B. B, C, D, and we want to integrate here inside. So what you do, first you can use this composite procedure method. So you split into pieces, right? And then we will use at each sum over the smaller rectangles and compute, and then you compute. You use this quadrature inside each piece. So essentially, what you do is, so for single element, single rectangular. So you sum over rectangle. I just don't want to simplify the formula. So you sum over the rectangle, and for each rectangle, all you have to do is that you use integration. You use this formula for integration with respect to first variable and with respect to the second variable. So essentially, it will be B minus A, C minus D. And then there will be two sums. Gx, Gy. Usually it's important to use the same m in x and y, so that because the order of the method will be, if you take different m's, different orders, the order of the computation will be the smaller one. So it doesn't. And then it should be alpha Jx, alpha Jy by f x Jx y Jy. Yeah, that's it. So this formula is just the same as you apply. You can check that this is the same as when you apply first integration with first apply Gaussian Quadrature when you integrate with respect to x. So you take the first sum, and then you apply, when you with respect to x, so you remove the first integration, and then you do it with respect to the second. So you give this another sum. So you get direct formula. So it's just a summation over m times m points within each square, each rectangle. And of course, this the same way you go to higher dimension. So 3-dimensional and so on. Okay, and no, coeficientes são em princípio, principalmente coefficients. You see, coefficients. Usually, coefficients are. You see, coefficients are different if the intervals are different. But usually, what in numerics you do, you first change coordinates so that you go to the standard interval, and then you use the standard coefficients that you know from that interval. So what I gave you the formula, they were from interval from -1 to 1. So what always you do for each integration, you change integration coordinate so that you change interval to -1 to 1, -1 to 1, and then coefficients are standard. So that's how you do. So you never recompute coefficients for every time for no new interval. You change integration variable so that integration interval is standard. And then I'll give you the short overview of what you will do. Is in the case of singular or indefinite intervals. So this is also often the case. So sometimes you need to compute, take the integration. Sometimes you integrate the function which has singularity, like something 1 over square root of x. 1 over square root of x, it's infinite at 0, but integral is perfectly well defined. Yeah? So, or another, if you want to integrate something on infinite, so from 1 to plus infinity. So it's another way. So how you do it? So there are different strategies. So I will just give an overview. So first is truncate. Truncate means that, for example, you can take an integral from 0 to 1 and assume that we have problems at 0. So then it can be written as an integral from 0 to epsilon plus integral from epsilon to 1. This one you compute, right? And this one you approximate. For example, take 0. And the same thing you can do if you substitute 0 by infinity. So from 1 to large number, you compute. From large number to plus infinity, you either approximate or just take 0. 0 is also approximation. Another is change variables. This is quite an obvious way. You always check for infinite interval integration, you can always change variables so that mapping the infinite interval to the finite interval. So only should be careful because when you change infinite interval to the finite interval, you can can get integration in finite interval, but with singularity. But sometimes so. But that's a way. Another way is a subtract singularities. Subtract. What does it mean? It means that if you integrate something where you know exactly what its singularity is, so you can subtract a function those integral you know, but it will cancel the singular part of the function that you compute. So that's often a trick. So essentially, this can be used when you exactly know what is the nature of the singularity and form of the singularity. Well, there is very nice way is ignore singularity. Well, ignoring singularity, for example, when you compute. For example, computing the integral of 1 over, let's take square root or cubic root. So ignore, do not take xg equals 0. Just don't put 0 don't put singularity at the points where you want to compute the function. So this usually converges very badly, but that's a way. So if you're lucky not to put point exactly the singularity or too close, then it may work. But convergence can be bad. And also there are smart ways. So like singular integration rules. So there are smart ways where there is a singularity of certain types. You can adjust weights or make something clever so that it will converge better and take into account that there is a singularity there. So that's a set of somewhat obvious ways how you can go for computing the other type of integrals. So next time we still address this issue of computing integrals, so I will be talking about this probabilistic way, so Monte Carlo method. So Monte Carlo method, where it used, so you see multiple integrals for 2 dimensions, you can compute it by taking more points in 3 dimensions and so on. So sometimes dimension can be very large, 100. So there is no way to compute it this way. So for example, then you can use Monte Carlo method. It's less, maybe less precise, but it's much more very effective. So computing it in some probabilistic way. So this we'll do tomorrow. No, tomorrow, next week. I think that's it. Yeah, that's it.